Welcome to the lecture number 13. So, in the last lecture we just have started discussing about the solvent effect on fluorescence, that means solvent effect on emission spectra, and we have taken the solid molecule that is responsible for the fluorescence, right, as like this. So, this is my solute molecule, right, having a dipole moment. So, I am just writing it over, denoting it over the plus and minus sign. So, the dipole moment could be mu e or mu g, depending on it is whether it is in the excited state or in the ground state. And so, the solvent molecules will going to be stabilize this solute, and because there will be a reaction field will be created by the solute molecule to the solvent, right. So, that reaction field R is the electric field in the solvent induced by the solute dipole, right. So, this is defined as the electric field in the solvent induced by the solute dipole, right. And as I mentioned the other day, that this R will be a function of the dipole moment mu, the radius over here, which is A, right, and the property of the solvent. Some molecule will be polarized more efficiently, some other not. So, that will be the property of the solvent. So, R is written as twice, there is expression of R twice mu by A cube into F, where F is equal to polarizability of the solvent, and A is the radius of the cavity, that means comparatively to the size of the molecule, right, radius of the cavity, right. Okay. So, now this polarizability of the solvent are two types, right. One is the electronic polarizability, another is the orientational polarizability. What is electronic polarizability? Suppose you have a dipole near to the solvent. So, the electrons of the solvent molecules are polarized, right. So, that is electrical polarizability, and the other one is the orientational polarizability. That means, if you have a charge species like water, let us say take an example of water. So, water, that O is partially negatively charged, H is partially positively charged, right. So, if you have a positive charge over here, which is solute, and water molecule is present like this way, because of the influence of this guy, this water will reorient, so that the final arrangement will be something like this. So, that is the reorientation of this water. So, this is called the orientational polarizability. So, I can write this F as a two term, right. So, that will be additive. So, first is F EL plus F OR, right. So, this F EL can be written as n square minus 1 by twice n square plus 1, right. So, this is the reorientation of electron in the solvent as it is instantaneous. So, where n is the refractive index of the solvent. Okay. And this F, right, that is the total polarizability. This is a function of the dielectric constant. So, this can be written as epsilon minus 1 by twice epsilon plus 1, right. So, eventually this F over is nothing but epsilon minus 1 by twice epsilon plus 1 minus n square minus 1 by twice n square plus 1, right. So, I can simply write F over is equal to epsilon minus 1 by twice epsilon plus 1 minus n square minus 1 by twice n square plus 1, where this epsilon is the dielectric constant of the medium of the solvent. So, this epsilon is dielectric constant, right. So, let us take this granted, because I am not going to show you in detail that how these things are coming, right. However, one thing is clear to me, that if the solvent does not have a permanent dipole, then F over is going to be equal to 0, right. Right. If the solvent does not have a permanent dipole, then F over is going to be equal to 0, right. And the solvation energy of the dipole, right. So, let me write here solvation energy of the dipole in the electric field. Which electric field? That electric field, no? R, this electric field. How to? So, this electric field, right, R can be written as delta equal to minus mu to R, right. This is the solute dipole, this mu is my solute dipole. Because it has created the electric field in the solvent, that R, the reaction field, so it will, that reaction field going to stabilize that solute, right. So, the delta E will be minus mu into R, right. Okay. So, now let us see that if I have a solute whose energy is Eg vapor in the ground state. Okay, let me draw over here. So, these are the ground and excited state of the solute, right, and this is in the vapor state, VAP, vapor state, and there is no solvent, right. So, if the energy over here is E G vapor and this energy is E E vapor, and I also said that this is the dipole moment of the ground state and this dipole moment of the excited state, and let us take this another condition over here. The condition is mu E is greater than mu G. So, I already have imposed this condition over here, that means the excited state dipole moment is more than the ground state dipole moment. Then in the vapor state, if I simply measure the absorption, I will get this much of energy transition, right. So, the new absorption in vapor, right, will be equal to new abs, right, that is the maxima. So, let us write max in vapor is equal to E vapor minus E G vapor divided by H, right, E vap minus E G vap divided by Planck constant. Okay. Now, if I put this solute in solvent, right, then as I showed pictorially while discussing the solvent effect on absorption, that this will be stabilized, this will also be stabilized, but the stabilization will be at the different extent, right. This will stabilize less, this will stabilize more, and we will get lower energy, right. So, let us see mathematically here, right, first. Okay. So, here let us say this energy is E g, is not it, and this energy is E E, right. So, solvation energy in the ground state, let me write that, solvation energy in the ground state is this much, right. Right. So, it is nothing but E g minus E g vapor, this will be equal to minus R into dipole moment of the ground state, so minus R dipole moment of the ground state, because the solute is in the ground state, right. So, R into mu g. Now, R has two component as I showed, right. Here R is 2 mu, here R is 2 mu by A cube into F, F is F E L minus F O R. So, from here I can write R equal to R E L plus R O R, which is equal to 2 mu by A cube F E L plus 2 mu by A cube F O R. So, I am going to use this equation from now and also this one, right. Okay. So, this is going to be equal to minus mu g R E L minus mu g R O R, right. So, I will just simply write the expression of R E L and R O R, right, which is nothing but 2 mu by A cube, right, 2 mu by A cube, and the polarizability, electronic polarizability and the orientational polarizability for R O R, right. So, let me write that minus mu g 2 mu by A cube is the radius of the cavity of your solute A, right, into F E L minus mu g 2 mu by A cube F O R. So, this mu that 2 mu by A cube, this mu is which mu? This molecule is in the ground state. So, that should be mu g, right. So, 2 mu g and this also 2 mu g, right. So, I will just write it as like this way. So, E g equal to E g vapor minus 2 mu g square by A cube F E L minus 2 mu g square by A cube F O R. So, I got this value of E g, right. Similarly, I am going to calculate the value of E E, right. So, I can write easily similarly in similar fashion, and E E minus E vapor is equal to minus mu into R, but in this case that mu is the mu E, the excited state dipole moment of this molecule. So, mu E into R, right. So, this is equal to minus mu E R E L minus mu E R O R. So, this is going to be equal to minus mu E twice mu by A cube F E L minus mu E twice mu by A cube F over. Now, the question is that which mu I should put over here. This is electronic change is very fast. So, that mu should be mu E. However, this is the orientational change, that is orientational relaxation. So, although I have excited this molecule from ground to excited state, but the solvent molecule which will see, right, the excited state just after the excitation, right, those molecules will take some time to reorient themselves. So, that means this reaction field, right, what we are going to have is very similar to the solvent arrangement in the ground state. So, this mu will be mu G, right. So, in this case REL is a function of, let me write clearly over here, REL is a function of mu E but ROR is a function of mu G. ROR is function of mu G because orientation polarization is slow, right, because orientational polarization is slow, right. Okay. So, then the rest of the part is simple. So, what I am going to have this equal to minus twice mu E square by A cube F EL twice mu G mu E by A cube F OR. So, I can write this as EE equal to EE vapor minus twice mu E square by A cube F EL minus twice mu G mu E by A cube F OR, right. So, now if I want to calculate that what is the absorption energy, right. Similarly, I have calculated over here, you see this lambda, look here, new absorption maxima vapor is like this, right. So, I have calculated. So, I can also calculate that new absorption in the solvent, right. So, that then I have to calculate EE minus EG, isn't it, EE minus EG. So, let's do it over here. EE minus EG is equal to EE vapor and from the other equation minus EG vapor, right, plus twice mu G square by A cube FEL plus twice mu G square by A cube FOR minus twice mu E square by A cube FEL minus twice mu G mu E by A cube FOR, right. So, this is equal to EE vapor minus EG vapor, right, minus I will take this 2 FEL by A cube, right, 2 f E L by A cube from here and from here, then this is equal to mu E square minus mu G square, right. So, then mu E square minus mu G square, and then I will also take minus 2 f O R by A cube mu G out, then this is going to be equal to mu E minus mu G, right. So, look at this term. So, I have already said or taken that mu E is greater than mu G, if you remember. If mu E is greater than mu G, then this quantity is a positive quantity. Let me change the color again. So, this is my positive quantity, this is my positive quantity, then the whole thing is negative, right. That means this energy is less than this energy, right, because the total thing is negative quantity. This energy is less than this energy means there will be a red shift in the absorption spectra. That means when mu E is greater than mu G, there is a red shift. That what we have seen with those model system, like while discussing the solvent effect on absorption spectra, right. We have seen, but here what we can see is exactly the same thing, but here more mathematical treatment I have shown you over here. So, when mu is greater than mu G, then I will see a red shift in the absorption spectra, right. Okay. Now, what I am going to do, I am going to give some time for the relaxation, right. So, as I said that once you have created this excited state E, right, the orientational polarization is slow. That means the solvent will take some time to solvate the excited state of your solute molecule. Electronic polarization is fast, but the orientational polarization is slow, right. So, once you create the excited state, it will take some time, the solvent will come and relax, come and relax. So, that extra stabilization of the state is because of the solvent reorientation, right, which is under the orientational polarizability of the solvent. So, now if I give enough time, then instead of using in the here, instead of using mu G for the ROR, right, for that E state, I will use mu E because I have given enough time for that, right. So, let us see what will happen for that. So, then in this case, this is the solvation energy for emission, right. So, solvation energy for emission, right. So, in this case EES, so let us say that this state, the energy of that state is EES, solve it, right. I just termed it like that. So, EES minus EE vapor, I can calculate that directly. Here the derivation will be exactly same, only the difference is that for ROR I am going to use mu E, not mu G, is not it. So, let me do it quickly over here. So, this is equal to minus mu E R, this is equal to minus mu E into R E L minus mu E into R O R is equal to minus mu E twice mu E by A cube F E L minus mu E twice mu. In this case I will write E not G, right, because I have given time. So, twice mu E by A cube F O R, right. So, this is equal to minus twice mu E square by A cube F E L minus twice mu E square by A cube F O R, right. So, I can write EES equal to EE vapor minus twice mu E square by A cube FEL minus twice mu E square by A cube F O R, right. So, I got that EES. Similarly, I will also have to get the EGS, right, EGS. So, that we can also do easily. So, I can write EGS minus EG vapor, right, EGS minus EG vapor. Let us do that over here. So, this is another important equation here. So, for that EGS minus EG vapor, this is equal to which state? Ground state, right. So, minus mu G into reaction field R. So, minus mu G into R minus mu G R E L minus mu G R O R, right. So, this is equal to minus mu G twice mu G by A cube FEL. This means that the electron has moved from LUMO to HOMO, right, excited state to the ground state, right. So, first electronic polarization is first. So, I use the mu G. However, in this case you see this mu G ROR, that twice mu by A cube, that mu, right, this is the orientational polarizability, but the solvent will stay as that they are in the excited state, right, because it takes time. Orientational relaxation is slow, right. So, in this case I will again use that mu E not mu G, right. So, this is twice mu E by A cube into F O R, and I am almost done over here. So, this is equal to minus twice mu G square by A cube F E L minus twice mu E mu G by A cube F O R. So, I can get this E G S equal to E G vapor minus twice mu G square by A cube F E L minus twice mu E mu G by A cube F O R. So, I also got this equation, right. I got this EGS, that is in the emission, after emission what is the energy of the ground state. I got this one EES, right, before emission, but after stabilization what is the energy of the excited state, and that is it. So, with this equation we will continue on the next lecture about what will be the energy of this emission, right. Thank you very much.